Welcome to the Problemers channel, season 3, episode 41, the episode which I titled How Generating Functions Can Solve Linear Non-Homogeneous Recurrence Relations, because in this episode we will solve precisely such a recurrence relation that you see on the left side of your screen. But before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from the material that we present on this channel is for you to go to the homepage of this channel, and at the top of that page in the channel's trailer section, find the episode titled The Problemers Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel, and that is for the most part solving problems in mathematics, physics, and computer science non-stop, forever and ever. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on this channel that resonates with you and use the comment section under that episode. Alternatively, you can go to the community section of our channel and ask your question there, and I'll take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current supporters and the current subscribers of our channel, especially the folks whom I know personally from Quora. Thank you very much for your support. And as one extra small announcement, because I'm being asked on a regular basis, how do I use this channel? In addition to the video material that answers this question and which I just described to you, I've put together a written document called How To, and the link to this PDF file is in the comment section of this episode. The objective of the mathematical problem S3E41 is to solve the linear non-homogeneous recurrence relation that you see on the left side of your screen over here, using the notion of generating functions. And here some of our viewers may say, Roman, why don't you use a characteristic equation or another helper theorem in order to knock out this recurrence relation? But the answer to that question is this is precisely the crux of the matter with this episode. I want to highlight the fact that in order to make mathematical progress, you need to have the ability to carry out two things. You need to be able to generate an idea first and then carry your idea through. Because if you cannot do both of these things at the same time, then it is highly unlikely that you will be able to make progress in mathematics, physics, or computer science. If you can neither generate an idea nor carry it through, that is absolutely no good to begin with. If you can generate an interesting idea but cannot carry it through, that is not a good enough situation. And if you can carry someone else's idea through, that is perhaps not too bad, but still this is not the ideal situation, because you want to precisely be able to do these two things: generate an interesting idea and then carry this idea through. And if we look at the pioneers of mathematics and physics, people such as, for example, Isaac Newton or Leonard Euler, they were exceptionally good at precisely these two tasks: generating an idea and then carrying that idea through and showing how exactly this idea can be materialized. And in order to demonstrate this point, we will solve the recurrence relation that you see on the left side of your screen using the idea or the notion of generating functions in all the details. And before we do that, a few words about the meaning of this recurrence relation and where did it come from. If you go to the home page of this channel and click on the courses tab, you will see the course that is entitled IGRP, Inversive Geometry in the Real Plane. This course has pronounced blue themed color. And in that course, in the episode number 20, under problem 21, we solved an interesting problem using the geometric transformation that is the subject of this course, the inversion of the real plane with respect to a circle. And in that problem, the setup was the following. We were given, shown in red, generating semicircle. This is a diameter of this generating semicircle. This is its circumference, and we named it S. The radius of this circle is R. And then into the planar region, trapped inside of the semicircle, the family of blue circles shown here, here, and here is inscribed as follows. The very first circle, S0, is inscribed in such a way that it touches the diameter of the generating semicircle at its center, the point O. I did not name it, but let's say I name it. This is the point O, and then it touches the generating semicircle S at the diametrically opposite point over here. Evidently, the radius R0 of that inscribed circle S0 is precisely 1/2 of R, and then into the remaining planar region that is trapped inside of the generating circle and outside of the first circle, an infinite family of blue circles is inscribed in such a way that each consequent or each next circle touches the previous one, such as S0, and it touches this previous circle externally, but touches the generating semicircle internally, the circumference of the circle and its diameter as shown over here, and smaller and smaller circles are inscribed into the generating semicircle in that fashion. And we define the numbers Tn as follows: as the ratio of the length of the radius of the generating semicircle R, this is the radius right here, from here to here, to the length of the radius of the corresponding inscribed blue circle, R0, R1, R2, and so on. In general, for any n greater than or equal to 0, the number Tn is defined as the ratio of the length of the radius of the generating semicircle and the length of the radius of the correspondingly inscribed circle. And in the problem, we are tasked with the objective to show that the numbers thus formed, T0, T1, T2, and so on, Tn, honor the recurrence relation that is shown over here. And it is evident from this particular setup, for example, that what is the number T0? Well, let's say the length of the radius of the generating semicircle is 1. 1 divided by 1/2 is 2, and there you go. This is number 2. And amazingly enough, for the second circle, we have the number 4, and on and on and on. And one of the quite interesting things that we witness in this problem is that when we deal with circles, we generally do not deal with numbers that are algebraic. Usually the number pi, which is transcendental, shows up. But in this case, we do not have transcendental numbers. And even forgetting about the numbers that are algebraic, we come to the numbers that are rational. And in addition to that, these numbers turn out to be not rational, but whole positive numbers, 2, 4, and on and on and on, when we will uncover these numbers. But it is actually quite an amazing thing that the ratio of this radii of the circle of this particular setup comes out to be positive integers. And now that we understand a geometric interpretation of the numbers Tn, we can take on the task of solving the recurrence relation that you see over here analytically. But do remember that in episode 20, while we solved the problem 21 in the inversive geometry in the real plane course, we solved this recurrence relation by using nothing more than the good old geometric transformation of inversion of the real plane with respect to a circle. I will throw in some more details as we go along, because In the process of solving this relation, we will come across the numbers that looks like this. Square root of 2 plus minus 1, and its close cousin, it will be 3 plus minus 2 times square root of 2. I will show what these numbers mean, where do they come from. But now that you understand that this particular linear non-homogeneous recurrence relation has a geometric interpretation that you see over here, an interesting question comes up. Is it the case that every linear non-homogeneous or maybe homogeneous recurrence relation that has this particular overall flavor where we have alpha, beta, gamma for coefficients that are sprinkled across the actual varying numbers? Is it the case that every such recurrence relation has a geometric interpretation? The answer to that question is, I honestly do not know. Maybe it is the case, maybe it is not the case, but this is something for you to ponder next time you take a shower or the next time you wait in the grocery store in the checkout line waiting to pay for your groceries. Since the lesson that we're trying to learn in this episode consists of two parts, generating an idea first and then carrying this idea through to fruition. Second, we want to use a baby recurrence relation that does not present any major computational challenges, that we can, on the one hand, evaluate or solve by hand, and then we can do the same thing, carry out the same computations using the ideas or the notion of generating function. And in this case, we will consider this baby recurrence relation shown over here. T of n plus 1 is equal to 2 times Tn with the initial condition T0 equal to 1. Again, the reason this is a baby recurrence relation because we can evaluate or solve this relation by hand by simply expanding all the intermediate terms. The term T1 is twice the initial term T0. The term T2 is twice the term T1, which we know from here. So this will be 2 squared. The term T3 is twice the term T2, which is basically 2 cubed times T0. The same thing for the element T4. This will be 2 raised to the 4th power times T0. So in general, the number Tn as a finite combination of elementary functions is T0 times 2 raised to the power of n. This is short and sweet, but in general, the more you do grown-up mathematics, the more you will realize that obtaining answers that are a finite combination of elementary functions, or the so-called closed formula, is a goal that is simply not achievable. Many times in more realistic situations, it is only possible to produce an implicit information about the solution that we're trying to obtain, but in cases when it is possible, this is how we do it. So the idea number one, how do we generate an idea that we will carry through? Well, the idea here is the following. First, we'll make a brave and a somewhat nebulous assumption that there exists a single variable real-to-real function, which we call generating function, g of x, that is analytic about origin, and the one that has a power series representation at the origin, which looks as follows. And this is the gist of the idea, that the coefficients in this power series representation of such an function, single variable, real-to-real, precisely match the numbers in the recurrence relation, with the idea is that here these numbers will be spelled out in its full closed formula glory as a finite combination of elementary functions. And that is what the answer to the question of what these numbers are. That is what the answer is. Again, in the big scope of things, this is not always achievable, but in certain cases when it is achievable, then that is how we do it. So that is the fundamental idea. So make sure you understand it, comprehend it, and maybe chew on it, dwell on it before you move on. First, we begin with the brave assumption that there exists a single variable, real-to-real function that is analytic at the origin, and the power series representation of that function has the coefficients that precisely match our numbers Tn, hopefully in the shape of a finite combination of elementary functions. That's step number one. Step number two, carrying this idea through to fruition and showing exactly how this finite combination of elementary functions can be achieved or produced, where the numbers t will be expressed as a function of the number n. Here we want to, on the one hand, step number one, we want to generate an explicit shape of the generating function gx, also hopefully as a finite combination of elementary functions. And once that is done, the step number two, we want to generate an explicit or concrete specific power series expansion of that function about origin. And then if we can do that, then in order to answer the question what these numbers tn are as a function of n, we simply as an answer read these coefficients off of the expansion of the function g of x about origin as the power series. So this is the overall theoretical plan. This is the idea. So how do we carry this through? Well, we will do that based on a popular recipe. In general, in generating functionology, this will be called ordinary generating function, but the idea here is this. First, we use the, how do we carry out these two steps? An explicit shape of the function g of x, and then the expansion. Well, here we use the DNA information that is baked directly into the given recurrence relation. In other words, this recurrence relation is the heart and soul of these numbers. The numbers that obey this relation, this is what they are, and we precisely capitalize on the given recurrence relation. We'll try to extract the DNA from it and generate the explicit shape of this function g of x as follows. First, multiply the equation that is given to you, the relation that is the recurrence relation, all the way through by one copy of x raised to the power of n. That is, you write t n plus 1 times x raised to the power of n is equal to 2 times t sub n times x to the power of n. Step number one. Step number two, sum this result over all legal values of n. Here you need to pay close attention to what these legal values are and work this idea through every time anew based on the recurrence relation that is given to you. In this case, the legal values will run from 0 to positive infinity. That will not be the case in our recurrence relation, but I'll talk about it in a second. So here we sum this result over n, t n plus 1 times x raised to the power of n from 0 to positive infinity, like that, equal to 2 times sum tn times x to the nth power, and again varies from 0 to positive infinity. We do it because the shape of the given recurrence relation is such that when n varies from 0 onward, there are no negative values for the indexes of the coefficient t or the power of n, because this is the nature of the Taylor series. The power series is such a series where the indexes and the powers are strictly not negative, 0 or positive. In mathematics, in complex analysis, for example, you will come across the so-called Lorentz series where the index n can be negative, and this is used to compute the values of residues of holomorphic function. The first such term where n is negative in the expansion and the Laurent expansion of the corresponding function will give you precisely the residue of the function at a particular pole. So here we use the initial value of 0 on both sides, and this initial value for the index n has to be uniform. It has to be the same all through the relation. So now the idea is to start sculpting the function g of x. Here, based on our brave assumption, what is this? Let's look at the right-hand side of the equal sign. What is this? Well, look at this. The index n in the coefficient t and the power n of the independent variable x, they vary at the same rate, n. So this is precisely the portrait of our generating function. So here we write right away 2 times g of x. Now let's concentrate on the animal on the left-hand side of the equal sign. How can we sculpt this material into something that contains nothing but the generating function g of x? Well, let's call this some sigma, just as a symbolic sugar. And let us spell out the first few terms. What does the sum sigma look like? Look over here. If n is equal to 0, then the indexes of the coefficients t, they run by one step ahead of the powers of x. So when n is 0, the index of the coefficient t is 1. So we'll have t1. I'll leave room over here. You will understand why in a second. Plus, when n is equal to 1, the index of t is 1 plus 1, 2, but the power of x is 1. So t2 times x. And the story goes on. t3 times x squared plus t4 times x cubed plus t5 times x quadrupled, and so on. So now the question is, by any which legal means, how can we manufacture from this material the material that contains nothing but our generating function g of x? Well, here in this case, the situation is quite merciful. We see if we multiply our sum sigma by one copy of x like so, then t1 will gain one power of x, and all the other powers will bump up by one. Square, cube, fourth power, fifth power, and so on. And what does that mean? That means that now, if we mark this power explicitly as 1, the powers of x and the indexes of the coefficients t match exactly. Look at this: 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5. What does it tell you? Well, it tells us that we almost have a complete portrait of our generating function g of x, with the exception of what? What is missing over here that will allow this formation to proudly carry the title of, yes, I am a generating function g of x? Well, the initial term t0. So if we add t0 to this formation, what will we have? Plus, we will have our function g of x. So this will be equal to sigma times x plus t0. You see? This is quite straightforward. And what does it mean? Well, from here it follows that for our sum sigma, we have the following result: g of x minus t0 divided by x. In some sense, some of our viewers probably could have done this maneuver by hand in their mind, just because we expand this function g of x in its series for the first few terms, and we see if we lop off the t0, divide by x, boom, we have this guy. So that is it. So now this sigma is equal to this expression over here, two copies of the generating function g of x. So g of x minus t0 over x. You see, it is important to understand that this equation over here, that is linear in the generating function g of x, is what? Is a byproduct of the DNA information that is baked precisely into this specific recurrence relation, not to some other recurrence relation, but this one specifically. In other words, in terms of the global if p then q implication, if this is the case, then necessarily this follows. You see, this is how we ensure that our function gx honors the contract, if you will, or is the result of the DNA information baked into the original recurrence relation. So now you understand this manipulation over here. Make sure you write it down or rewind this video if you have to. I will erase this material here because we will need the room. And now what do? Well, we solve the equation that is linear in gx for gx. How do we do it? Let's do it this way. Multiply x through, so move x from the denominator of the right hand side to the numerator of the left hand side. So what you will have, 2 times x times our function g of x, you see, is equal to g of x minus t0. Agreed? So now we move t0 to the left, 2 copies of x times gx to the right, flipping the signs, and what do I have? t0 is equal to g of x minus 2 times x g of x. G of x is present in both summands, so it becomes g of x times 1 minus 2 of x. You see, and from this equation, we write down the explicit formula for g of x. It is equal to t0 divided by 1 minus 2 of x. See, this is how we carry through our idea. Remember the first step, the explicit shape of the function g of x as a finite combination of elementary functions. Eventually you will realize this is a miracle. Most of the time it's not possible, but if it's possible, that's one way to do it. And this is it. From this point onward, any which legal means you're aware of, generate the power expansion of this function about origin, any which way, directly by the Taylor formula, derivative, coefficient, yada yada. But eventually you will realize that the more you work with these functions, the more you will not do that. You will have a stack or a library of expansions already, and what you will do, you will manipulate the existing decompositions into submission in order to obtain this result. And in the future we will see how this can be done, but here it's straightforward. It's our favorite infinite geometric series, so we write it down like this. N varies from 0 to infinity, and we suggestively write the coefficient like this: t0 times 2 raised to the power of n times x raised to the power of n. And now, as I promised to you a few minutes ago, we read the numbers dn directly off of the expansion. In other words, this right here is precisely our numbers tn. This is how generating functions take care of business. And what is this? Look at this. Do you see anything familiar? Yes, you do. We obtain exactly the same answer, but using the notion of generating functions. So this is the idea. A brave assumption that there exists a single variable real-to-real function g of x that is analytic at the origin, and the coefficients of this expansion exactly match the numbers in a given recurrence relation. That's number one. And number two, use the DNA information built into the given recurrence relation in order to manufacture an explicit shape, the power expansion, and then from that power expansion simply read the numbers tn, hopefully as a finite combination of elementary functions or the so-called closed form formula. So in this way we can rewrite it suggestively as follows: as a function of n, t of n is equal to what? t0 times 2 raised to the power of n. And this is our answer. Now that you understood, maybe you can watch this segment a couple times before you move on, but now you understand the overall premise, how the generating functions take care of business. Let us move to our case. Wonderful. In our case, we're given the following linear non-homogeneous recurrence relation. Tn is equal to 6 copies of Tn minus 1 minus 1 copy of Tn minus 2 minus 4 with the initial conditions, T0 equal to 2, T1 is equal to 4. In this case, solving a recurrence relation is fundamentally not that different from solving a differential equation, where we're given an equation and then the initial conditions. These are our initial conditions. And maybe just to make sure, if you're watching this for the first time ever, I mean, if you're dealing with the recurrence relations for the first time in your life, then LNH, linear non-homogeneous, means the following: all the numbers Tn, all the variables, are in the first powers. It is not the case that this one is squared, this is cubed, or this is quadrupled, or whatever. And then a homogeneous relation will be without the free-floating term. With the free-floating term, this will be non-homogeneous relation. And remember that in this case, again, we assume that for this particular recurrence relation, there exists a single variable real-to-real function that is analytic at the origin, and it admits a power series expansion that has the following shape: Tn times x, and this is our basic theoretical idea. And here the numbers Tn, the coefficients in the Taylor series expansion of the mystery function g of x at the origin, matches precisely these numbers over here. So if we manage to produce a finite combination of elementary functions that sits over here, we'll simply read the numbers Tn off of that expansion. Once again, remember, we do two things. We discover the explicit shape of the function g of x once, and then number two, we unzip this function into its power series about origin. So to that end, remember, the first step, We multiply this relation through by 1 copy of x raised to the power of n. I pre-wrote it on the board for you because you already know this step. Every term is multiplied by xn, 1 copy, honoring the coefficients. Of course, remember the information that you're given in the particular recurrence relation is basically the DNA of that relation. And that's what makes this relation unique in this relation. Not some other relation, but this specific one. So we honor all the material that is given in this relation. And that is how we do it. We multiply all the summands or all the terms in this relation by 1 copy of x of n. So here maybe I'll show it to you with the green here, xn, 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 and 1 copy of xn. And now what do we do next? Remember from the previous segment, we sum all these products over the legal values of n. And here I want to test your understanding of what do you think these numbers over here should be. I specifically did not write down these numbers because I want you to fill in these numbers. What is your idea? Now, if you said that here we sum from 0, as shown over here in the power series portrait of the mystery generating function g of x, then you fail. This is not correct. Why is that? Remember, in the Lorentz series, yes, we're allowed to have negative indexes and powers of z in general, but in the Taylor series we are not. So if you put n equal to 0, what you will have over here? T sub minus 1, and over here you will have T sub minus 2. Again, in the Lorentz series, this is admissible, this is allowed, but this is not Lorentz series, this is Taylor series. That means you cannot sum here the carry out the summation starting from 0, and you cannot carry it out starting from 1, because here 1 minus 1 will be 0, legal, but here 1 minus 2 minus 1, this is not allowed. So what is the actual initial value of n that must be used across all these summations? Well, the correct answer is 2. So we start from n equal to 2 in all summation, n equal to 2, n equal to 2, like so. Now, there is a reason why I decided to do this recurrence relation this way, because many times what students will do is the following. They will iterate the given relation by what? By 2 steps rightward. In other words, if we replace n with n plus 2 uniformly, and that is precisely what is meant when we say iterate the relation rightward twice, increase the value of n by 2, what we will have here? We will have t n plus 2. As a matter of fact, let me write this material for you guys in a different color so you see what's going on. T n plus 2. You will have it on the right, on the left hand side, and then what will you have? You will have 6t n plus 1 minus t sub n, and obviously you will have minus 4. You see, if you iterate this relation, this recurrence relation rightward once according to this substitution, then you will obtain this. If you multiply this by 1 copy of xn, and then you will sum, then you will be allowed to carry out the summation starting from 0, because if n is equal to 0, nowhere in this relation you will have negative indexes or negative powers. But the thing is, and this is completely legal maneuver, but I wanted to show you that even if you do not do that, still the result will be exactly the same. Whether we carry out the summation like this or carry out the summation like this, the result, the explicit shape of the function g of x, either way will be precisely the same. 2 different paths, 2 different lines of reasoning a little bit. The reasoning will differ a little bit, but both reasonings will terminate at the same shape of the function g of x. And as a matter of fact, as a good exercise for you, once you see how I do this, how I solve this recurrence relation using this particular approach, taking the given recurrence relation head on without any special adjustments, I suggest that you do it with this approach, and once you obtain the same shape of the generating function g of x, well, after that you can already merge to the line of reasoning that I will produce later on, but this is the idea. And now We will chew on all these pieces one by one, because remember, what is the objective now? The objective now, the big objective now, is to manufacture the explicit shape of the function g of x. And we will do that by working with each sum and sculpting that sum into the material that contains nothing but the function g of x and the independent variable x. Very good. Now that we obtained our main workhorse relation over here, I rewrote it on top of the board. We want to work on it piece by piece until we sculpt a material that can be solved for the generating function g of x. And to that end, we will begin with the rightmost object over here, 4 copies of this sum. Don't forget that the index n of summation still runs starting from 2. I explained why in the previous segment. So here, how do we manufacture the material that contains nothing but the generating function g of x and or the independent variable x? Well, this is almost our favorite infinite geometric series, one that runs from, let's use another chalk over here, maybe this one starts from 0. You see, this starts from 0, xn, but the one that's missing, how many terms? The first 2 terms, so minus x raised to the power of 0, 1, and minus, when n is equal to 1, minus x, so minus 1 plus x. There you go. So what does it tell you? It tells you that we have the following result: 1 divided by 1 minus x. Here we flip from the power series representation into the explicit shape of the function, minus 1 plus x. And what is this? 1 minus 1 plus x times 1 minus x over 1 minus x. What is this? 1 minus 1 plus x squared over 1 minus x. 1 and negative 1 cancel out. And what do we have in the end? In the end, we have the following result. Our sum is equal to x squared divided by 1 minus x. You see, this is the manipulation, and there you go. So what we can do now is erase this sum and replace it with the material that we uncovered so far. So this will be 4 times x squared divided by 1 minus x. Wonderful. Next, we will chew on our recurrence relation starting from the left and work on this object over here. What is this? Sum of t sub n times x raised to the power of n, where n runs from starting from 2 to positive infinity. So what is this? Well, this is, again, quite straightforward. This is our function g of x that is missing 2 first terms, because again, the powers of x and the index of the coefficient in the power series expansion of our function go in step. They match each other. So this is minus t0 minus t1x. This is what it is. But we know this particular number, so here we have g of x minus 2 minus 4 times x. This is it. This is quite straightforward. So now over here, instead of this sum, let's write down the intermediate result that we obtained so far, and you will see that this is how we work on this relation step by step. Minus 2 minus 4 copies of x, and now we just have to deal with this sum and with this sum. Wonderful. Let us now work on this expression over here. Apparently I forgot to make sure that the index over here is tn minus 2, but what is it? Tn minus 2 times x raised to the power of n when n varies starting from 2. What is it? Well, let's write down the first few terms. When n is equal to 2, the index, the subindex of the coefficient t is 0, but the power of x is 2. So now this is how this dynamic dual works. If the index is 1, then the power of x is 3. When the index here of t, of the coefficient t, is 2, then the power of x is 4. When this is 3, then x is 5, and so on. So now the question is, how do we manufacture the material from this sum that contains nothing but our generating function g of x and or the independent variable x? Well, this is quite straightforward over here. This sum is quite merciful. We see that this copy of x squared is an extra 1. So if we factor out that copy, if we write it down as follows, look at this. If we write it down as x squared times, then what do we have? t0 plus t1 times x plus t2 times x squared plus t3 times x to the third plus, and so on. And what is this material? Well, this whole thing is our function g of x. So not our sum is equal to x squared times g of x. You see, this is what's going on here. And now we can erase this sum right here. Carefully erase it. And we will write down the result that we obtained so far, minus x squared times the function g of x minus this. So now we only have to work with this sum right here. Wonderful. So what is this sum over here? Well, in order to spell it out in terms of material that contains nothing but the generating function gx and or our independent variable x, we write down the first few terms of that sum. When n is equal to 2, then the index of the coefficient t will be 2 minus 1 is 1, t1, but the power of x will be what? 2. And this is the lockstep in which these two factors work. The difference between the power of n and minus n minus 1 will be 1, and off it goes, plus t2 times x to the third plus t3 times x to the fourth plus t4 times x to the fifth plus t5 times x to the sixth, and so on. So what do we do over here? Well, first look at this. We can make sure that the powers of the independent variable x go in step with the index of the coefficient by factoring out one copy of x. Look at this. So we can write it down as follows: x times, and then in the parentheses we will have t1 times x plus t2 times x squared plus t3 x cubed plus t4 x to the fourth plus, and so on. And what is this? What do we recognize in this expansion? Well, this is a partial expansion of our generating function g of x, which is missing what? If we add the initial index to it, the initial value of t0 to it, then this will be our function g of x. But if we added one term, we have to do what? We have to subtract another one, t0. So what do we have here? Here we have the following: x times g of x minus t0, just like that. And because we know the name of t0, this is x times g of x minus 2. This is basically, let's spell it out, x times g of x minus 2x. This is our sum. So this is this. So let's write it down, but now we have the coefficient, we have the factor of 6 in front of the sum. So here, let's do this. Here we have 6 times x times g of x minus 12 copies of x minus the rest of the material. And what do you see now? Well, we see now that we have on top is an equation that is linear in linear in the function g of x. Let me highlight it for you. G of x, where is another one? G of x and g of x, and all we have to do now is solve this equation for g of x. And over here, I do not want to insult your intelligence. This is middle school arithmetic. We simply gather all the material that pertains to the generating function g of x on the left-hand side of the equal sign, let's pretend. So it will be x squared with a positive sign. It will be minus 6x plus 1. So this is your factor right here, x squared minus 6x plus 1. And we carry all the other material on the right-hand side of the equal sign, 2 with the positive sign, plus 4x minus 12x minus 8x minus the far right term over here, 4 copies of x squared, or 1 minus x. Bring everything to one denominator. Again, this is just middle school arithmetic. And the result is the following. It turns out that all the material over here is in 2 copies. So if we factor that number 2 out, then we will have 2x squared minus 5x plus 1. Don't forget over here, minus 2x minus 8x minus 10x. 2 factored out minus 5x. 2 copies of 2 explains this plus 1. And 4x squared, look at this. We have 8x squared minus 4x squared is 4x squared, 2 factored out. There you go, nothing complicated. And once we divide everything by this square factor, by the quadratic, we have our result. We managed to achieve our goal number 1. Remember, we wanted an explicit shape of the function g of x as a finite combination of elementary functions, and this is precisely what we have over here. And the next step is to use any which legal ways, any machinery that you know of, or however you can in a legal and mathematically sound way, to produce, to unfold this into a specific Taylor series expansion about origin. And you will develop a nose for doing so in the most efficient manner with time as you work more and more with these decompositions. And here, if you work with these functions long enough, you will see that what you have here is a combination, a finite combination of actually 3 functions that are geometric series in these guys. And the way we unmask this fact is by working with the quadratic term in the denominator. Remember that over the field of real numbers, we can always represent such an expression as a product of either terms that are linear in x or at most quadratic, because over the field of real numbers, it is not always possible to factor such quadratics further. The coefficients here in such a quadratic equation are real, and if such an equation has at least one complex root, it means that the complex roots for this expression come in conjugate pairs. Both roots are complex numbers, no real roots, so this expression will be left that way, but as is. But in this case, we can actually factor this quadratic further, and the way we do it is as follows: by solving the following quadratic equation: x squared minus 6 plus 1 equal to 0. Recalling our favorite formula from middle school, we have minus b, so 6 plus minus square root of b squared 36 minus 4 32, so minus 32 square root divided by 2, and there you go. We represent 32 as 16 times 2. Square root of 16 is 4. 4 divided by 2 is 2, and there you go. We have our 2 roots, 3 plus minus 2 square root of 2. So now the symbols x1, 2 will stand for specific real numbers. Let's make it official. The root x1 will correspond to the plus, and the root x2 will correspond to the minus. So let's write it down over here. X1 will be 3 plus 2 square roots of 2, and x2 will be 3 minus 2 square root of 2. And what does that mean? That means that our function, generating function g of x, can be now represented which way? 2 times 2x squared minus 5x plus 1 divided by 1 minus x times x minus x1 times x minus x2, because this is how, once we have these roots, the most senior coefficient here will be 1, and once we carry out this multiplication over here, we see that that is the case. So this is the way to factor x squared minus 6x plus 1 comes out to be x minus x1 times x minus x2. You see, we replace the quadratic with the product of its factors, and there you go. This form of the generating function lends itself naturally for what? For the partial fractions decomposition, which we carry out as follows. And if you know how to decompose such functions into its partial fractions representation, you can skip this segment and the next few ones. But for those who are not familiar with this process, it works as follows. Because the multiplicity of each real root x1 and x2 is 1, these factors x minus 1 and x minus x2 come in the first power. The factor 1 minus x also comes in the first power. Then we represent this function as the sum of the following ratios: a over 1 minus x plus b over x minus x1 plus c over x minus x2. And now our objective is to determine the values of the constants a, b, and c. And the way we do it is a way good to be familiar with that approach, because you will see it on and on again in complex analysis, for example, where you will be coming up with ways to compute residues of holomorphic functions at certain poles. So the idea here is the following. We multiply both sides of this representation by one of these denominators, 1 minus x, x minus x1, x minus x2, multiply through. Such a factor will cancel out only in one place. For example, if we multiply all the terms in this equation equality by 1 minus x over here will cancel out. I'll show it in a second, and it will cancel out only in one place here. And then we evaluate the result at precisely x equal to 1. So let's write it down. So we have 2 times 2x squared minus 5x plus 1 over, let's see, we have 1 minus x times x minus x1 times x minus x2. That's how it works. And then we multiply this. Remember, we multiply this by 1 minus x. So far, so good. Now, what will we have on the right side? 1 minus x in the denominator, 1 minus x in the numerator will cancel out. It will be a. So let's say we'll mark it with red, a, just to make sure we keep it that way. Then what we will have? We'll have b over x minus x1. But then it will be multiplied by what? 1 minus x plus we will have, let's see, we'll have c over x minus x2 this way, and then multiplied by 1 minus x. You see, 1 minus x. That is very straightforward. Now what we do is we evaluate both sides of this equality at precisely x equal to 1, and this at x equal to 1. What will happen over here? Well, look at this. 1 minus x in the numerator, 1 minus x in the denominator will cancel out. When x is equal to 1, what will happen to this factor? 1 minus 1 is 0, so this will be 0. 1 minus 1 is 0, this will be 0. And then this is how we automatically, in some sense, obtain the value of the coefficient a. So the coefficient a, the value of the coefficient a, of this constant a, will be what? It will be 2 times 1 squared minus 5 times 1 plus 1, because remember, at x equal to 1, we replace all the variables x uniformly with this specific value, 1. And then we will have divide by 1 minus x1 times 1 minus x2, you see? But x1 and x2 are specific numbers. For example, 1 minus x1 is equal to 1 minus 3 minus 2 square roots of 2 is equal to what? Minus 2 minus 2 square roots of 2. So far so good. And what is 1 minus x2? Well, it would be 1 minus 3 plus 2 square roots of 2. What is this? This is minus 2 plus 2 square roots of 2. And this is it. At this point, this becomes basically a mundane middle school number shuffling. And if we carry out the computations carefully, then we will obtain the following. Exactly 1, and again, this is not too complicated to see. We have 2 minus 5 minus 3 plus 1 minus 2. Minus 2 times 2 is negative 4. Here we have, look at this, 2 times square root of 2. We carry out the minus sign, plus 2, and the same thing with the minus 2, two conjugate numbers. And we factor out 2, we get negative 4 in the denominator, square root of 2 plus 1, square root of 2 minus 1, minus 4 cancel out. And what is this? This is a plus b times a minus b, a squared minus b squared. Square root of 2 squared is 2, minus 1, 1, 1 over 1, 1. And this is it. The value of the constant a is 1. And we repeat the same experiment for the constants b and c. For the constant b, in order to determine the value of the constant b, what will we be multiplying the whole thing by? X minus x1. And what will we multiply this equality through in order to determine the value of the constant c? X minus x2. And cancel things out, and then in this case we will evaluate the left hand side of this equality at x equal to x1, and we know what the value of x1, and we will do the same thing for the case of x2. Multiply everything by x minus x2 and evaluate the left hand side of the result when x is equal to x2. In slightly more detail, in order to determine the value of the constant b, when we multiply our equality that you see on top of the board by what? By x minus 1, that factor in the numerator will cancel out with the same factor in the denominator. That is why over here you will not see that factor in the denominator of the modified version of the generating function gx. You see it's gone 1 minus x and then x minus x2. And then we evaluate this expression at the value x that is equal to the first root x1. So over here, over here, over here, and over here, instead of x, you will uniformly substitute the value of x1, which is what? 3 plus 2 square roots of 2. And on the right-hand side of this equality at the same time, this copy of x minus x1 will cancel out with the 1 in the numerator. The constant b will remain. Here we will have one copy of this expression. Here we will have one copy of this expression. And both of this expression and both of these expressions will vanish when x is equal to x1. This will be gone, and b will remain. And that is why you see this expression over here, b equal to. Again, once you do the arithmetic, it is not complicated. You will have the following result: negative, don't lose this minus sign, 3 plus square root of 2 over 2. The same exact idea applies to the determination of the value of the constant c, this time on the left-hand side of our modified generating function. The copy of x minus x2 will cancel out with the 1 in the numerator, and then we will evaluate whatever remains at x equal to x2 as shown over here. X equal to x2, don't forget. And what will happen at the same time on the right-hand side of the equal sign? Again, the x minus x2 factor in the denominator will cancel out with the 1 in the numerator. We will have one x minus x2 here, one copy of x minus x2 here. But when we evaluate this side at x equal to x2, this will vanish, and this will vanish, and only this will remain, and that is why we have this result. And once you carefully do the arithmetic, you will have the conjugate. Look at this. Our roots are conjugate, and these numbers are conjugate too, which is in some sense was to be expected. Minus 3 minus 2 square roots of 2 over 2. And over here, just to give you something for a reference with the correct response. When we do x minus x1 evaluated at x2, for example, this guy, here we will have the difference of the roots, and in this case 3's will cancel out, square roots of 2 will survive, we will have -4 copies of it, and so on. Once you unwind this expression, this is precisely what you will get. The same thing over here. Instead of x2 minus x1, you will have x1 minus x2. The same deal applies. Same thing over here. It's not complicated again. This is not even mathematics. Remember that mathematics is the time when we spend while we're generating ideas. This is at most computational calisthenics. We generated idea way back previously at the beginning of this episode, and now we're carrying our idea through. So this is not mathematics. These steps are very straightforward. Zero intellectual voltage. This is computational calisthenics. And now what do we have? Well, now we know the values of these coefficients, so now we can represent our original generating function as follows. Our formerly mysterious generating function g of x is not mysterious anymore, because now it can be represented as follows: 1 over 1 minus x minus, don't forget we carry the -3, plus 2 square roots of 2 over 2 times x minus x1, and this is 3 plus 2 square roots of 2 with the minus, everything becomes minus. Here -3 minus 2 square roots of 2 divided by 2 times x minus 3 plus 2 square roots of 2. Don't forget we have the difference here, plus and minus, plus and minus, plus and minus, plus and minus. And now it should be more than obvious why we did all this work, because now basically we see that our generating function gx is basically a combination of 3 geometric series, and we know how to decompose all these series into the underlying power series representation, and we will work on this string of functions left to right, starting with the classical geometric series on the left. Nothing extraordinary over here, with one little caveat that usually when we deal with generating functions, we treat all the mathematical objects that we deal with in a purely utilitarian fashion, and we throw all the analytic caution, if you will, to the wind, because normally we would need to worry about the disk of convergence, uniform convergence, this and that. All these ideas and all this theoretical apparatus of the theory of analytic functions pretty much flies out of the window. We only want the tactical material that is allowed by the power series representations of functions, and all we do here is the following. Now we substitute the power series representation into the general view of our generating function, and we write it as follows: g of x is equal to sum of, let's write it suggestively, 1 times xn, where n varies from 0 to positive infinity. Now we work with the middle function over here, this one, and we massage it as follows. We write -3 plus 2 square roots of 2 divided by, now let's do this carefully, factor out the -1 from the parentheses over here. What we will have? We will have minus turning into plus. We will have 2 times, and then we will have 3 plus 2 square roots of 2 minus x. You see, all we did is factored out -1 from this parenthesis, and this -1 collided with this -1 and generated a plus. So there we have it. And now what do we do? Well, we're setting things up for a traditional infinite geometric series expansion of our function here, and we factor out this particular term out. So we get 3 plus 2 square roots of 2 divided by 2 divided by 3 plus 2 square roots of 2. And what do we have here? 1 minus x divided by 3 plus 2 square roots of 2. Would you agree? All we did is we factored out our first root. Cancel, cancel, and what can we say about the reciprocal? The reciprocal of 3 plus 2 square roots of 2 is clearly what? We multiply this by 3 minus 2 square roots of 2 and divide by 3 minus 2 square roots of 2. A plus b times a minus b is a squared minus b squared. A squared is 3 squared, 9. This guy squared is what? 4 times 2 is 8. 9 minus 8 is 1. So this whole thing collapses into 1. And this becomes 3 minus 2 square roots of 2. So now we represent our function as follows. 1 divided by 2, 1 minus x times 3 minus 2 square roots of 2. Isn't that wonderful? Can we expand this function into its power series about origin? Sure, yes we can. What is the result? The result is the following. Sum over n from 0 to positive infinity, and we suggestively bring all the material in. Look at this, we have to bring all the material in because this will become our future element of the numbers Tn. And then 3 minus 2 square roots of 2 raised to the power of n times x to the power of n. Do pay attention over here that the minus sign, due to the fact that we factored here -1 out, the minus sign became the plus sign. So now we have the plus sign over here. So far, if we replace this material with what we have so far, we will obtain the following. Plus, pay attention to the plus, the sum over n from 0 to positive infinity, 1/2. This is 3 minus 2 square roots of 2 raised to the power of n, x raised to the power of n, and all we have to do now is deal with this function over here, but we will deal with it in exactly the same way in which we dealt with its conjugate cousin, and we'll do it as follows. X minus 3 plus 2 square roots of 2. Here again we factor out -1 from the parentheses, and what do we have? This -1 collides with this -1, generating a plus, so we have 3 minus 2 square roots of 2 divided by 2 over 3 minus 2 square roots of 2 minus x. Then again we factor out the second root, 3 minus 2 square roots of 2 over 2, 3 minus 2 square roots of 2 times 1 minus x divided by 3 minus 2 square roots of 2. And we can be brave already. Cancel out root x2, cancel out root x2. And what is the reciprocal of this root? Well, you should already know that much, that we multiply this by the conjugate image. 3 plus 2 square roots of 2. 3 plus 2 square roots of 2. We again obtain the same a squared minus b squared. 9 minus 8 is 1. This guy remains, so this is 3 plus 2 square roots of 2. So this is equivalent, so we can write down this expansion right away. Sum over n that varies from 0 to positive infinity, 1/2. And then what? 3 plus 2 square roots of 2 raised to the power of n times x to the power of n. Isn't that wonderful? So now we substitute this expansion into this. Don't forget again that the negative sign became the plus sign. We have the plus sign over here. So this is plus sum n from 0 to positive infinity, 1/2, 3 plus 2 square roots of 2 raised to the power of n, x to the power of n, and voila, we have a nice power series representation of our generating function about origin, as we claimed a few minutes ago. And we are basically done, because in this case we can see that all three infinite series converge. They all run from the same boundaries over the summation index from 0 to positive infinity, and we know that this functional series converge because this is how we did the overall decomposition, so we can merge all of them into one. Once we merge them into one, then you see the representation of this function over here. I wrote suggestively the material in the middle in square brackets, and square brackets do not carry any other meaning. This is not a floor, this is not a ceiling, nothing like that. This is just for as a visual candy to separate the material in front of x and the independent variable x by itself. And we see that since I wrote it in red, this is precisely the idea that I put forward at the beginning of this episode. Once we obtain a concrete or a specific decomposition of our generating function into the Taylor series, into the power series about origin, we simply read the numbers Tn off of that series as the coefficient in front of x raised to the power of n, and here it is, written suggestively, and t as a function of n came out to be a finite combination of elementary functions. This is, eventually you will learn that this is basically a small miracle. This rarely happens, but when it does, this is how it works. T of n is 1 plus 1/2 of 3 plus 2 square root of 2 raised to the power of n plus 1/2 of 3 minus 2 square root of 2 raised to the power of n. I wrote these numbers for you over here. Let's see if I can find the same color. Maybe not. This way right here. So T0 is 2 we were given, 2, 1 is 4 we were given, then 2 is 18, 3 is 100, 4 is 578, 3,364, 45, and so on. There's actually a lot of interesting stuff going on between expressions like this, but this is perhaps for a separate discussion. One thing I wanted to bring your attention to before we wrap up with the problem S3M22 is the material that is available in my free book, Inversive Geometry for All. The corresponding chapter you can find in my free GitHub repository. All these discussions are there. This is this material for those who did not read the book. And the link to that chapter is in the comment section to this episode. You may investigate on your own, but it turns out that geometrically, we come out to the ratio of square root of 2 minus 1 to square root of 2 plus 1 as rho designated in my text. This is obviously we recognize as 3 minus 2 square roots of 2, because we again multiply these expressions, this ratio by square root of 2 minus 1. We have 1 in the denominator and this expression in the numerator. There is a geometric meaning for this when 3 minus 2 square roots of 2 raised to the power of n. For example, this specific term over here. For algebraic thinkers, this is just an algebraic expression that doesn't really mean much beyond the meaning of the symbols in it. 3 minus 2 times square root of 2 raised to the power of n. But in the corresponding geometry of the situation, remember, I spent a little bit of time at the beginning of this episode telling you about a geometry of this particular recurrence relation. It turns out that this number, 3 minus 2 times square root of 2 raised to the power of n, comes out to be basically the length of the radius of the nth reflected circle. Once we solve this problem using the reflection of the real plane with respect to a circle. Remember, we had the original setup was like this: generating semicircle, then circles, the family of circles inscribed into it. So here we the circle of reflection that solves the problem geometrically actually starts over here. It runs the entire diameter of the generating semicircle. So the circle goes this way. And then the reflection with positive power works. So once we flip all the circles in this circle with positive power, then we will get another family of circles, and the length of the radius of such nth reflected circle signified with the prime over here comes out precisely to this number. So this is how these numbers gain a geometric meaning, and we understand that these numbers, of course, are the reciprocals of each other, so we can write this formula in some other way if we wanted to. But again, in my travels in integral calculus, we have this wonderful result that the definite Riemann integral from 0 to pi over 2 of x times dx over sine of x plus cosine of x comes out to be pi square roots of 2 over 8 times the logarithm of 1 over this number right here. So this is also how mathematics works. We notice something interesting, we start digging, we start investigating. Maybe something interesting comes out of it, maybe not. But the thing is, you never know until you try. Now, this is it for the mathematical problem S3M22, and we will move on to a new challenge next. Very well, our next challenge will be another problem in mathematics numbered S3M23. And in this problem, we're given a circle and n distinct points shown in this electric greenish blue color on the periphery of that circle, on its circumference, and distinct circles. The question is, how many chords will be formed if all these points are connected? And most interestingly, not how many, but why. This is an interesting question. Why that many? Why your answer is what it is? Obviously, we want to hear your story behind the answer of why. And in the next episode, I will present four solutions of my own, and one of the solutions will be actually revolving around precisely the idea of generating functions. So you may want to think on your own how this problem can be solved using the notion of generating functions that we discussed in this episode. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present 4 of my solutions of the mathematical problem S3M23.